our number system. Real numbers. Okay, so small reminder about this. Oh, I need a pen to write. This is the real number system. Every real number falls into one of two categories. And then we get even more specific about our rational numbers and can label them as integers. So all integers are rational numbers and are real numbers, but to be an integer you have to meet specific requirements, right? And then within the integers is another group of numbers called whole numbers. And within the whole numbers, another group of numbers called the natural numbers, like the counting numbers, 1, 2, 3, 4, 5. Okay, so natural numbers are like 1, 2, 3, 4, 5, etc. Whole numbers are 0, 1, 2, 3, 4, 5, etc. Integers are -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, etc. in both directions. Rational numbers are any number that can be written as a fraction. Irrational are the ones that are never-ending, non-repeating decimals, and those are all part of the real number system. Okay. So this whole, we get this negative in the radical, we can't finish any calculations with it. So there comes places in different careers or different branches of mathematics where you need to finish that calculation in order to then get to the answer, and the answer still makes sense, even though it appears that we can't get through that calculation. So in order to make that happen, we add on to our current number system a set of numbers called the imaginary numbers, which makes all of this together, the real numbers plus the imaginary numbers, called the complex number system. So real numbers are technically complex numbers also, just like how rational numbers are real numbers, okay? But what makes a number complex is it could be just imaginary, it could be just real, it could have a real part and an imaginary part, and we'll look at that too. Okay? All right, so what are these imaginary numbers? Where did they come from? How did they come up with them? All right, so basically, we have this problem. The reason we can't take a square root of a negative is because no number squared ever comes out to be a negative value, right? Because negative times negative in our real number system is positive, and positive times positive is positive. So if you have the same number, there's no way to square it and make a negative. That's an issue at certain places, and we're going to let you guys do a little research about where those places are on your own. So basically, they determined this new unit, I. Okay? I, imaginary number. And they wanted to revolve everything around I so that if you squared it, it turned out to be negative. That was the idea. We can't take square roots of negatives because we don't have anything that you square that becomes a negative. So let's name this new thing the imaginary number I, and when you square it, make it a negative. Okay? So they didn't make it like -5 or something like that. That would make it difficult to work with. So they just called it like a unit, like 1. But so that when you square it, you get -1 instead of +1. Okay? What that means is that I by itself is representative of the square root of -1. Okay? So when you see I by itself, that meant you had a negative in the radical. Rather than leaving it in the radical and writing it like that, we write it as I. Okay? So then what is I squared? This is how they actually made the system, right? What did we already say? I squared is going to be equal to -1. So this is the reason this works and why it worked out okay that they added this onto the number system. Though it's a new set of numbers, it connects back to the real numbers, right? This is an imaginary number, but when I square it, I get a real number. Okay? Oh, speaking of which, I have a shirt. It's really old, so I don't wear it. But it's really funny. It's a joke. See, it says get real. And it says 1 plus 2i times 1 minus 2i. So we'll see if we can figure out why that's funny by the end of the day. My sister thinks it's funny that I wore it to the grocery store. I figured whatever. People either have no idea what it means, right? Or they get it and they're like, that girl's dorky for wearing that shirt, but that's funny. Okay? And that's okay. All right, so if we look at I cubed, let's look at the pattern that works with these imaginary numbers. So I'm going to think of I cubed in my head. If I tried to break it down, to a more understandable format, would you guys agree that it would be okay to say that I to the third power is the same as I squared times I? Okay? But what's the value of I squared? -1. Which means this is really like having -1 times I, which means I to the third power simplifies very nicely to just be -I. So notice that the imaginary numbers are not using they didn't make this whole new thing like, oh, new rules and new this. They just defined a new unit, basically. But I'm using the same exponent rules that exist with my real numbers, right? So when I look at I to the fourth, would you guys agree that it would be okay for me to think of I to the fourth as I squared times I squared? Okay. Then what is I to the fourth equal to? 1, because I squared times I squared is -1 times -1, which means I to the fourth is 1. Interesting. Over here off to the side, just to show you guys how cool this really is. I'm sure you think it's just as cool as I do. Okay. If I had, so this is my favorite one right here. I to the fourth is just 1. It's even simpler than I squared, which was -1. So not only does it turn back into a real number, but like a beautiful real number as far as like multiplication and stuff goes, 1, right? So if I'm trying to think about I to the fifth, in my brain, I'm going to think about it as I to the fourth, right, times I. What would that simplify to be? What is I to the fourth? 1. What's 1 times I? I. Oh, goodness. So I to the fifth is the same as I. Interesting. Okay. What about I to the sixth? So I could think about that as I to the fourth times I squared -1. Oh my goodness. Okay. All right, what is this? This is why it works. So it's like this crazy big idea, like, wow, you just changed the whole number system, you threw this in there, and then it's like, but it's so simple in a way. Like, it creates something for this, but the way it connects back to the real number system is so amazing that we can actually do calculations and get between both and use it for things. So I to the seventh is like I to the fourth times I to the third, which is going to turn out to be what? -I. So I to the fourth is just like I to the seventh is just like I to the third. All right, and then what about I to the eighth? Is going to be like I to the fourth times I to the fourth. I could just write it like this if I wanted, right? And it's going to equal 1. Okay, so here's the thing. If I'm multiplying some stuff together with I, what should be my expected outcome? It's kind of a limited amount of things I would expect. I, 1, -1, -I. Okay? So at least it's doable. Okay, so let's do this guy. I to the 231st power. That's fun. Okay? Now remember how we've been viewing everything. We've basically been viewing everything in a form where we would kind of have something and then simplify it. Jason? Okay, so how did you get -I? Okay, so you divided it by 4. So here's why that would work really well. I would like to know how many I to the fourths are in there, right? Just like how I to the 8th was I to the fourth squared. Because I to the fourth is 1. So it just makes that really, really, really easy for multiplication. So how many I to the fourth are there in 231? You don't need a calculator. Okay, so there's 57, but then there are 3 left over. So to make a power of 231, I'm going to write this lower because I messed up my space, sorry. To make a power of 231, I'm going to use I to the fourth 57 whole entire times. And then I'm still going to need to use 3 more powers of I, because 4 times 57 is not going to make 231. It's going to almost make 231 if you added 3 more to it. So then I'm going to have I to the third. What happens to this I to the fourth to whatever power it's raised to? It's 1. right? This is the beauty of using I to the fourth, right? That's why it's my favorite, all right? So it's 1. If this is all just equal to 1, 1 times I to the third is just I to the third. Now I do have to know what I to the third is. It is negative I. So yes, Jason, you were right. Okay. And now I can see why you divided 231 by 4. Do you guys get why he used that? Okay. So 231 divided by 4 gave him this. This didn't really matter because these 57 powers of I to the fourth will just turn into 1. This was super important, right? It dictated how much was left over, which told us what our final answer would be. All right, so what about I to the power of 120? Good, okay. So that's going to be I to the fourth 30 times with nothing left over. So 1 to the 30th power is just going to be 1, okay? Or I could use Jason's method. I could do 120 divided by 4. I could see it went in 30 with a remainder of 0 and know that 0 is the power I would put, but anything to the 0 power is equal to 1, okay? So this means if you divide by 4, your remainder is always going to be 0, 1, 2, or 3, which is telling you which power of I to use. 0 is the same thing as I to the fourth because it will turn out to be 1. And then the power of 1, 2, or 3 would dictate one of these other answers. Okay? Is this all right? Okay. Imaginary unit. Lots of fun. All right, so how would we write rad negative 24 using this? So basically, you're going to use the skills you always did, and then you're going to tack onto it this meaning of the imaginary number. Basically, the square root of 24 is 1. This is true, right? Two numbers underneath the radical, you can multiply them together underneath the radical. They equal negative 24 under a radical. What is this worth? I. Break this down as we normally would. Okay, so we would either build a factor tree or we would look for perfect squares. So 24 is 4 times 6. So 4 is a perfect square. The root of 4 is 2. 6 has no more perfect squares in it. So it would remain underneath the radical. So it's basically I times 2 rad 6. And how you would see them write that is like this. 2I rad 6. They generally write the I after in between. My theory is because if you put it at the end, it's hard to tell if it's in the radical or out of the radical. I is very skinny. Okay. Are we okay with this? So now in the quadratic form, if we're using quadratic formula or completing the square, and they said find the real solutions, and we got the negative under the radical, we would stop. But if they just said find all the solutions, when we got the negative under the radical, we would simplify using this method right here. Okay? And so there would be an I in our answer as part of the imaginary number. All right, so we can solve equations like this. All right, let's look at part B together. That's what we're going to do. All right, let's solve it by completing the square. Okay, a little review. Okay, is 5 the number that we want there if it's a perfect square? No. Okay, so I'm going to move 5 to the other side. And I don't want x to have any coefficient, so the negative needs to go. Okay? What number would I add here to complete the square? Ashley? Good, 4. Okay, remember you take the middle term with our b value, our 4 there, divide it by 2, which would be 2, and then square it, so I want to add 4. And whatever amount I add to one side, I add to the other side as well. So this will give me x minus 2 squared. This will give me negative 1. Now I can solve this equation by doing what? Square roots. Okay, that's the purpose of making perfect squares, is to be able to use square roots. So if I square root both sides, I'm going to get x minus 2 equals plus or minus, same thing as before. And how am I going to write the square root of negative 1? And then just like before, I still need to get x alone because it is not alone. So what do I need to do? Add 2. So here's the thing with these numbers. This is a real part and this is an imaginary part. They cannot combine together. You saw how they're in separate parts of the system. But we can still write it as a 2 real part being added and subtracted with the I imaginary part, and those are our solutions. So these are 2 complex solutions. One of them is 2 plus I, and one of them is 2 minus I. This is all right? Okay, so you can still solve the same way. You just might have some weird looking answers. If it asks for real solutions, none. If it asks for all solutions, here you go. These 2. Okay? All right. How to work with I. We're going to start at B. It's the same as A, but it has a subtraction sign in the middle. Okay? So this is just like combining like terms in pre-algebra and algebra 1. Okay? Imaginary parts can combine with imaginary parts, and real parts can combine with real parts. Think of this as minus 4 and minus 2I. And then these parts weren't affected by that. And then I'm just going to combine together real terms and imaginary terms. So negative 6 and negative 4 combine together to be negative 10 as the real part of the number. Negative 2, negative 2I will combine together to be negative 4I as the imaginary part of the number. All right, nothing new there, right? Just treat the I just like you would treat it as if it were a variable like x. All right, how do we normally multiply quantities together? FOIL, right, or the distributive property. So we're totally going to do still that same thing. All right, so 5 times negative 4 would be negative 20. 5 times negative 3 would be negative 15I. So is everybody okay with that part? So real and complex, they can multiply each other. That's okay. I is just another factor. So I had a factor of 5, a factor of 3, and a factor of I kind of get all multiplied together. Then negative 7I times negative 4 would be positive 28I. And negative 7I times negative 3I would be positive 21I to the second power. So the thing is, there is a couple more steps here than normal, because besides the fact that you need to combine like terms right here, 13I as our imaginary part, we have this negative 20 here. The reason this is going to take a little more simplification than before is when this was just x, it was x squared, and we didn't know what x was, and that's fine. But I stands for the imaginary unit, and what is the value of I squared? Negative 1, which means I can actually simplify this more. This is like having 21 times negative 1 right here, which means it's really like I have negative 20 plus 13I minus 21, and the negative 20 and the negative 21 are real numbers, okay? And so this is like negative 41 plus 13I. All right, so FOIL is not new. What's new is you need to recognize that I squared is worth negative 1 and continue simplifying the problem. Is that okay with everybody? Or? Yeah, they tend to write them like that. Yeah. All right, so this one's like my shirt, my Get Real shirt. Okay. So can anyone predict what's going to happen in part D here, this multiplication problem? Michelle? Yeah, so everything is either going to get canceled out that's imaginary or transformed to real, which is why my shirt says Get Real. See why it's funny now? Okay, yeah, fine, okay. All right, math jokes, all right? So 4 times 4 is 16. 4 times positive 3I is positive 12I. Then negative 3I times 4 is negative 12I. And negative 3I times positive 3I is negative 9I squared. What happens to the middle two terms here? They cancel out, okay? It's just like having 4 minus 3x times 4 plus 3x. The 12x's are going to cancel out. That's because we multiplied by what we call the conjugate. So if you don't know that word, make a little note here that these are conjugates because they have the same first term, a different sign before their second term. okay? So those are called conjugates. So what happens every time we multiply together two conjugates is that the middle terms get canceled out, because since the numbers are the same, we're always getting the same value, one positive and one negative. Now, because I squared is so special, I squared is really worth negative 1. Notice that at this point, there is nothing imaginary or complex left in my problem. Okay? So this is like 16 plus 9, which is just 25. So this multiplication problem between two complex numbers that had imaginary parts turned out to be 25. Okay? This is why the imaginary numbers become valuable, because they connect so well back to our system. All right, which brings me to the last thing we have to do. Just like with radicals, okay, when you guys simplify fractions, we only want, okay, rational things in the end in the denominator. So we don't want radicals. Is an imaginary unit rational? No, it's not even in the real number system, okay? So that is, again, is something that we wouldn't want in the denominator. Okay? So look at part A when you just have 7i in the denominator, and we know that we can multiply a fraction by 1, which means same numerator, same denominator. It's okay for us to have imaginary units or radicals in the numerator. We just don't want to see them in the denominator. What would we choose to multiply by so that 7i becomes real and no longer has that imaginary part to it? Samantha? Yeah, so we can actually multiply by any version of I. Okay? The simplest thing is to just use I, not negative 7i, just I. If you multiply by the others, that's fine. You just might have to reduce some stuff at the end because you're multiplying by extra factors. So in the denominator, we're going to get 7i squared. That's what I wanted, because I squared will transform to a real number. And in the numerator, this I is going to distribute to each of the terms in 8 plus I. So I'm going to have 8i plus I squared. Remember that each I squared is negative, which means my numerator is like negative 1 plus 8i. I usually write it in this direction. That's why I'm doing that. I usually put the real part than the imaginary part. And in the denominator, it's really like I have 7 being multiplied by negative 1. So negative 7. Solution written like this negative could be taken and divided each of these terms. Look like a negative 8i over 7. This is probably how you would see a because to leave the negative in the denominator is a little bit like not simplified. It's kind of excessive. So what about part B? Can I just multiply by I? No, that would help the 2i. It would all of a sudden be 2i squared, and that part would be real. But then the part that was real, the 3, would now be 3i, and it would be imaginary. So how did we take something, think about my shirt over here, my funny shirt. How do you take something that has a real and an imaginary part? What can you multiply it by so that it becomes completely real? Savannah?
3 plus 2i.
Good. We use the conjugate, okay? So this said 3 minus 2i. I'm going to use 3 plus 2i because we saw what happens when we multiply together the two conjugates, right? The terms with I cancel out, and the term with I squared turns into a real number. But whatever I do in the numerator or denominator, I have to do in the numerator as well. So then we just have a lot of multiplication to do. So I'll simplify and you guys simplify. Hopefully we'll get the same thing. This is going to be like 9 minus 4 times negative 1 in the denominator. In the numerator, 15, these combined together. And this is like 4 times negative 1 there. So in my numerator, it's like I have 15 plus negative 4. So I'll be 11 plus 16i. And in my denominator, it's like I have 9 minus negative 4, which would be like 9 plus 4, or 13. And just like with the quadratic formula, if there's a common factor with 11 and 16 and 13, we can reduce this. But if there's not, then we would leave it alone. So 11, 13, and 16 don't all have some common factor. So this would be the simplest form to write that. So no new method of solving, but the fact that if there is a negative under the radical, there is a way to deal with it. Okay. The way I works, really important to remember that I squared is -1. However, it adds, subtracts, multiplies, and all of those things, just like things that you've seen in our real number system before. Okay? All right, so